traveling from Durban to Dubai, Dubai to Delhi, and Delhi to Lucknow, Lucknow to Kanpur, reached here at 12. Just I was thinking that in what way I should have a talk for this kind of August gathering. So I just tried to compile the slides which are related to integration of carbon and hydrogen, need for the future and the need of the refinery when we talk about in terms of a sustainable climate change and environment challenges. So all of you know this, I need to talk much on this, that energy security is our prime objective and how to achieve the sustainable and greener processes for developing this carbon neutrality technology and the product for the future is very, very important and challenging. When we talk about the per capita growth, right, you can see the number here, 0.6 tons of oil equivalent per person, which is the energy per capita as of today, and we would like to reach to a level of 1.8 tons of oil equivalent per global average. So this is where the difference, and we need to look forward that how this can be achieved in future. And 4 trillion to 12 trillion, that is again our motive, right, how to achieve this. That is again a big challenge for the future, and all of us, scientists, researchers, all of us have to work. But at the same time, when you talk about the need of the fossil derived feedstock versus the greener technology, there is a huge gap. So we import most of the oil, all of you know more than 90% of this crude oil is imported even now. And how can we avoid that? How can we get it out this? And that the number that coal will also remain in future. So coal to hydrogen, coal to liquid, by using the sustainable carbon capture technology is also the need of the future, and we need to find out how this can be done. And this is where the static synthesis of hydrogen energy to meet the demand, including the fossil derived feedstock, is also we have to consider. So this is what you see, the drivers for the change when you talk about the broader picture of India petrochemical demand. So all these petrochemical feedstocks, ethylene, propylene, methanol, xylene, benzene, butadiene, all these will be required as per the needs for development of the product. And those who are chemical engineers, those who are working in the chemistry area, they know that what would be the challenges in terms of achieving this when you talk about clean chemical or clean refinery concept. So this is a huge, I think, the demand which is increasing exponentially, and we have to meet this demand in future by finding out the ways that how this can be made sustainable and by finding out the technology of carbon capture. So there you see that, right? This type of ups and downs, that is where you see the key roadblocks for the net zero future. So we have to look at process integration, process optimization, electrification, all these electric vehicles which are also coming up in future. We have to look at the process development and scale up for electrocatalytic routes. Catalysts will play a role in the future in terms of the sustainability, and artificial intelligence is very, very important. So the pace of technological advancement and the economic and social viability versus the resource efficiency, all these will be very, very important for the future. And we need to find out how can we find a way where the low carbon or carbon feedstock transition with respect to the available resources which are green and sustainable for the future, this can be achieved. And that's why they need to work on this diversified, renewable and sustainable energy sources with the small modular nuclear reactor. So miniaturization of the reactor system is also very, very important feature. Instead of using the large reactor, we need to find out the tabletop type of reactor system, and that would also be required, I think, in future, and we need to find out the way how can you achieve this kind of economical and social viability product from our available resources. So let's see the complexity of the refinery of the future. This is where we have to utilize all kind of feedstock, not only the fossil feedstock, but all kind of feedstock as well as the available resources. So this is where the refinery is facing the challenges for the future, and we need to expand the portfolio of energy and multiple carbon streams which is required for the future. So there will be the biomass, there will be the kind of the feedstock like the coal, natural gas, and several other kind of the low carbon feedstock which can be used for future, and we need to use them effectively because this is the need of the hour when we talk about that how we can make the entire product. This is the kind of the table which you see here. The challenges are in terms of the the networking of this kind of the raw materials, their availability and the type of the feedstock and converting it into the product with efficiency. So the low carbon product with high efficiency and what kind of reactor design will be required, that will be challenging for the future. So when you talk about the carbon dioxide utilization, carbon-based product, you need to find out the hydrogen availability also, because the refinery is facing again a big challenge in terms of the availability of the hydrogen at an economical price. The water splitting, everybody talks, electrolysis of water, but these are, as of today, 350 rupees per kg of the hydrogen. Practically, it is not feasible. We need to get the hydrogen at a rate of 150 to 180 rupees per kg. So that is when you see that the biomass gasification, pyrolysis, or something like that, the water splitting and get the green hydrogen, integrated with the refinery intermediate, so partly replacing the grey hydrogen, and that can be converted to blue hydrogen. So that is also the hydrogen produced will be by the different processes and capture the carbon dioxide and utilize the carbon dioxide effectively for the process, and that's kind of decarbonized feedstock will be required in future. So green hydrogen target, when we talk about the around 8 lakh crore, that is the kind of expected investment by 2030 on green hydrogen, and that is the requirement of 10 million metric ton of green hydrogen, and that's why the green hydrogen versus the green ammonia, these will be another important. The fossil import, that is again another target, that how can they reduce the fossil gas feedstock, so which is of 1 lakh crore. And again, there is a target of 50 million metric ton per annum, that's what again by 2030. So this is to be reduced or cut down by 50%, and that is when we need to integrate between the green hydrogen versus the hydrogen which is being derived from the fossil gas feedstock. So all these things that you see here, scope 1, right, which is a kind of reduction, to scope 3, which is in between 1 to 3, I will just talk on that. So that is where how can we integrate the 1 to 3, and in what way we can find out the process for hydrogen development. So these are the 3 scopes. So 1, 2, 3 and 4. So there can be in between several other scopes, right, which can be a combination of these two. That is the, you can have the something which is the refinery conversion, you can hydro crackers which are already traditional one, steam methane reforming which is also being done. So that is the traditional one, but the scope 2 would be a kind of indirect energy emission, which could be based on the electricity from the grid, natural gas and crude oil, and scope 3, which is the indirect energy emission, and that is where the use of conventional fuel, road transport, industrial construction, but at the same time the carbon capture is very, very important in this. So we need to find out that how can we reduce the carbon dioxide from the different processes and get the kind of renewable power generation for utilization of the carbon dioxide or low carbon product. So this would be a challenge for the future, that so this has converted this process and then converting it into the carbon dioxide which is captured and converted into different kind of feedstock. So that is a need for a decarbonization for the future, and different factors will be included from the process refinery, which is the carbon emission, and the order of magnitude of you know that 3.4 billion ton of the carbon dioxide is already there, and 1/3 of the carbon dioxide is to be reduced by 2030. So that's kind of way by which we need to find out the way, and lot of policies are to be made in order to achieve this target. So I'm not going in detail of this type, the carbon capture schemes of refineries and features, but when we talk about the emerging science and technology and the branches of science and engineering, where they need to work for the chemists to apply chemistry and even the researchers. We need to do all these kind of tactics. So a lot of work is being done on reverse molecular reaction, because that is also need of our in order to integrate the process of hydrogen and CO balance within the system. So we need to work on this. Direct air capture is another very important. Carbon capture and utilization, then gasification, pyrolysis, and repolymerization, and there are different kind of waste material like plastic that should also be integrated into the system. So plastic plus biomass combination as a co-pyrolysis, that is also required for the future research. And then all these products like related the diesel, kerosene, functional molecules, polymers, the spark, but these should come from your raw materials which are either coming from the waste or which are coming from the resources which are available as a form of, in the form of biomass, plastic or other kind of feedstock. So the carbon mitigation has become a big challenge in fact when we talk about, and approaches of carbon mitigation also different, and different approaches can be used depending upon the kind of the complexity of the system. So multiple approaches is required. One of solution cannot be the complete solution for all the purpose. So one thing is the carbon evidence. Everybody talks about that, right? The changes to reduce the fossil gas feedstock, and which is practically difficult because we are dependent on the fossil gas feedstock. So one of the ways is try to get the blue hydrogen or something like pink hydrogen, which are also coming up nowadays. So different color codes of hydrogen are there, but accordingly the cost of production of these will also increase. So we have to make a balance on that. So grey hydrogen to blue hydrogen, which is just like an example of you get the hydrogen from biogas, you get the hydrogen from natural gas by decomposition also. So that kind of carbon can be utilized effectively, but cost of hydrogen production will be very, very challenging. Second thing is the carbon inverting, which is also being practiced, like CO2 utilization to reduce the fossil feedstock, and that is also being done by several, right? But you see the carbon dioxide, we capture it and hydrogenate it and convert it to methanol, dimethyl ether, and we also have developed one of the technologies on coal to methanol with the support of the Department of Science and Technology and the Thermal as a partner, and we did this 1 ton of coal to methanol, and that coal in highest coal, 40% has coal, and converted into methanol. And the same process, the CO2 which is coming from that plant is being integrated into the plant, same reactor itself, converting that CO2 also to methanol and dimethyl. So those kind of technologies are need of the future in order to convert this carbon dioxide. And the third one which is still here is carbon removal, and that is CO2 capture and permanently storage. So that is also possible and can be done. So I think a lot of R&D is required in this area also, where the energy can be taken from the solar or alternative sources, because the cost of conversion, cost of the process is very, very important. So CO2 capture and storage, CO2 capture and convert it. So carbon capture and utilization, I think that is one of the important for the future. So a lot of things are again when you talk about the minimizing the carbon footprint. So we need to work in those areas like the design of the novel catalyst, reactor design, process optimization, and a lot of the characterization tools will be required. And that's why the applied chemistry is very, very important when you look at the entire process development, and then machine learning and carbon neutrality, high throughput DFT calculation, molecular dynamics. So these are already being done by different academicians and researchers. So dynamic changes in terms of monitoring the in-situ activity practice programs, and all these things are the needs, right, which are required by integrating the different universities or researchers or the integrate with the international body. So this is where I think there is a need of the hour where different groups should come together and find out the ways that how these can be developed. And this is where now good tools now you see that photovoltaic light, water electrolysis, hydro, right, when you talk about complex single state electrolysis technical process, the range of the photochemical reactors. So these are also, the conversion is less, but these can be scaled up because the cost is also less in this process. So scaling up is a big challenge with water, nitrogen, carbon dioxide, and all these can be taken through photochemical or photoelectrochemical. So device and the product design will depend on the what kind of surface it developed there, and on which you can have the electron transfer and the reaction can be taken. So this is also very important for the future and R&D requirement. So there is a critical need when you talk about. So I am not going in detail of this, but these are like industrial flue gas, right? These can be CO2 capture and converted, syngas, right? You can have a selective, right, CO2 separation, and then all these can be converted by CO2 hydrogenation to methanol, methanol, dimethyl ether, olefins, and sustainable aviation fuel, which are also required for the future. So all these things are very important for the future research, that design and commission and operate this kind of carbon capture and utilization plants. So all these are being done from 1 TPD to 5 TPD. Plants are already working on these areas, and we need to take into the future. There are some of the thought process also, because how this reverse water gas reaction and CO2 hydrogenation can be integrated. So there in between also challenges in terms of so XLG analysis is required, Your thermodynamics is very, very important. So from fundamental to applied research, as they have made it to the common side, that is where I think young generations have to work in this area. And cost of hydrogen is very, very critical because the hydrogen economy, that will give the solution for the counterproduct. Otherwise, the CO2 conversion to chemicals will not be successful. All it depends on the cost of the hydrogen, and that should be in situ also within the system, that how this hydrogen can be generated and utilized for the process. So there are different kinds of approaches, and I think some of these are already being done at R&D, but this should be worked through process intensification, and this is again the need of the hour, whether it is region or diphenol or olefins, that they should be worked in these areas. Now people are working on non-thermal also, right? Because the advantage is that if you want to go for ammonia synthesis, typical, right, the Haber-Bosch process, which is a very high process, very high temperature, that can be done just at atmospheric pressure also. So now these kind of use that where you can change this kind of, right, the law of thermodynamics also by using this kind of the high temperature plasma, non-thermal plasma, and this is also where the research is required. And already again the research is being done in this area. We can work on this. The olefins can be produced, green ammonia can be synthesized from this, and this is again that CO2 to olefins or CO2 to SAF can be done under these conditions. But these are in practice scale and need to take it to the next level by developing more and more research in this area. So that is again one of the ways by which we can convert this nitrogen and hydrogen into ammonia or CO2 hydrogenation into the olefins, which are thermochemically require very high temperature, very high pressure. But under these conditions, we can do the reaction at the lower temperature and lower pressure. Biomass, everybody talks, right? We have 230 billion metric ton of biomass which is available, right, for energy purposes, and that can be utilized again. So how the biomass can be converted to hydrogen or refuse derived fuel, all these municipal solid waste which contains the 55% of this biodegradable component can be converted to the refuse derived fuel, and biomass plus this RDF, this can be again a source of the power which is already being done, but it can be a source of hydrogen also for the future. And there are also, right, lot of these things are done. We are also working on this combustible 1 TPD biomass to hydrogen plant, and this can be done biomass to bio-oil and reforming and biomass gasification. And again, we need to calculate the energy process, energy consumption in both the process, whether pyrolysis will be suitable or gasification. Now again, it depends on the how much is the availability of biomass in that local area. So low amount biomass pyrolysis will be better and convert oil into SAF, or large chunks of the biomass you can do the gasification, and that can be done again. So these are some of the thoughts, right, in what way we can capture the energy of the carbon and utilize it. So membranes are coming up again in a big way, and we can integrate this process. So I'm not again, right, just in short that the membrane will have the advantage of suppression of the two gases and carbon dioxide and other gases, and this can be also be used for the selective membrane to capture process and work on it. And there is a need, right, where we talk about all this, how the data collection will be done, right, so physical twin and data twin, and how can we integrate the entire process, and this is where the industrial support is required, and AI for the refining, by the already in the industrial internet of things, IoTs are coming and people are working in this area, and I think we need to take the advantage in terms of the information, decision, control, maintain, and predictive research framework. So these are again the areas for the research for the generation. Cost is very important, as I said, total energy. So when we talk about thermocatalysis versus electrocatalysis, you can see the difference 125 to 400 rupees per kg of kilowatt hour per kg per product versus 35 to 100 kilowatt hour per kg of green hydrogen. So that is again, we talk about 150 rupees per kg of hydrogen. That is the, I think, the optimal if we can get versus the 350 to 400 rupees, which is quite high and not acceptable by the industry. So we need to work on these areas. So finally, before closing, I will just look at these things that all these, the research is very important in terms of material science, advanced material science and development of these kind of materials, which will take all the like deep understanding about the different kind of matters. So artificial intelligence, data science, or one-plus simulation will play a big role in selecting these kind of methods, because data are available, collect the right data and use it for the future research that is important, but when you look at all these right process innovation and integration, so innovation is required all these kind of fundamental research to apply and then take it to the next level. And this is, I think, policies are also to be made when we talk about the CO2 capture, hydrogen production, and making the entire process sustainable and that is need of the society. So we need to work in all these areas. Not reading all these things, but you see that all these initiatives are being done, right? And all these technologies, when we talk about the energy analysis, is also being done. But I think at some level, the policy is also to be made that what kind of resources are available, how can we collect it effectively, how can we utilize it effectively. These are also challenges for the future. I stop myself here. Thank you very much for providing me the time and the opportunity.